we can use mine. Okay, yeah. Sure. So should I start it? Stop.
Yes.
Okay. Hello everyone. So today I'm going to present the second part of the chapter 3, which is coding attention mechanisms. Yeah, a few weeks ago we learned how to build a simple attention mechanism. Yeah. So with the trainable weight, like to trainable ways to project the input to queries, key, and values. So this week we are going to add the causal attention into our pipeline, and also we'll stack the causal attentions to build the multi-head attention. Um, so so why do we need causal attention? So the causal attention mechanisms ensure the model only factors in tokens that occur at or before the current token in the sequence. So let's take this sentence as an example. Your journey starts with one step. When the model look at the first word, we don't want the model to see the tokens after the itself. So we want to block the information after your. So in this case, our goal is to make the elements in the upper triangle of the matrix to zeros. So this is our goal. So how to do this? So the first step is to um, replace the elements in the upper triangle of the unnormalized attention scores with the negative infinity. So why negative infinity? Is because that after we pass the negative infinity to softmax, the value will become 0. So yeah, this is the first step. We replace the elements in the upper triangle with negative infinity, and then we apply softmax. And then as you can see on the bottom, the elements became 0 after applying softmax functions. So the second step is to enhance the generalizability of the model. So we will add some dropout. We'll add the dropout layer, which means that we will randomly drop some values in the attention weight. So yeah, as you can see at the bottom, yeah, some of the values are dropped. And then finally, we want to stack the causal attention mechanisms in order to build a multi-head attention. So the multi-head attention allowed the model to have multiple views or representation of the input sequence. So yeah, you can see in the figure we stack in this example we have two heads. So that means we have the input vectors will be projected into two queries, two keys, and two values. And then at the end, we'll have two context vector for one input. Yeah, then the final step is to concatenate the two context vectors together to build the final context vectors. So the simple way to build the multi-head attentions is to just simply stack them. So in other words, we calculate the queries separately one by one. So in this example, we have two heads. So we project the first query using the first weight and second query using the second weight. So they are computed separately. But we can do this more efficiently by combining the weights together first. So we project the input using the combined weights and then obtain the combined queries and then split them at the end. So we have after the splitting we have two queries here. So it's the same for keys and values. So for here we just take the queries as an example. So let's just see the code first. So yeah, in this code, we can see that we are trying to fill the upper triangle with negative infinities. So firstly, we create the mask using the torch upper triangle functions. So what this function does is that it creates a matrix that has ones in the upper triangles. And then we apply the other function called mask fill to replace the ones with the negative infinities. So yeah, we can get the final product like this.
But generally in this project, we are trying to like.
Yeah, and if we applied, so after we apply the softmap function to the results, we'll get the final attention weights. So yeah, as you can see, the upper triangle is replaced with 0 so that the model cannot see the future tokens. And then adding dropout to the attention weights is pretty simple. We just call the torch dropout layer. Yeah. So here we have, we instantiate the dropout layer, and then we create an example of ones, a matrix with ones, like has a size of 6 by 6. So after we fit the example to the dropout layer, we got the result. But you may wonder why it is 2, because it is scaled by the factor of 0.5 because the dropout rate was 0.5. So yeah, simply it's like this using this formula. So if we change this to let's say it's 0.75%, it will become 4. So yeah, 1 minus, so it's 4. Yeah. So we can do the same to our attention weights. Okay. So let me go back to the okay. So let's move on to the multi-attention heads. So this is the class of multi-attention head, but you may find it very overwhelming because it's very complicated. The metric manipulation is pretty complicated. So I make a summary here. So in this example, we have batch size of 8, and the contact size was 4, and the embedding size was 256, and we have 2 heads in this example. So originally we have an input X with the size of 8 by 4 by 256, and we project the input with the weights for query key and values. So we have query and key and values with the same size of the input. And yeah, we implicitly split the query key and values by reshaping. So in that way, we have 2 heads. Yeah, so it's just a reshaping. So after reshaping, we have query and key and values with the size of 8 by 4 by 2 by 1 to 8. So yeah, after we have this, we do a transpose for the query key and values for later matrix multiplications. And so yeah, so we transpose the second and the third dimensions. So we'll have query and key and values with the size of 8 by 2 by 4 by 1 to 8. And then we also do another transpose for the keys. Yeah, so you do the transpose at the third and the fourth dimension for keys. So we'll have 8 by 2 by 1 to 8 by 4. So the purpose is that because we want to do the matrix multiplication of query and keys, so that the dimension will match. So after we do the matrix multiplication of query and key, we got the attention weights with a size of 8 by 2 by 4 by 4. Yeah. And then we will do the matrix multiplication between the attention weights and the values. And we get the context vector with the size of 8 by 2 by 4 by 1 to 8. And we transpose the second and the third dimension back. So the number of tokens will be in the second dimensions. And then we'll reshape. We collapse the third dimension. So we will have 8 by 4 by 256, which is our final context vectors. Yeah, it's kind of very complicated. So if you have any questions, yeah.
Any comments or questions to this part? Right, so all this transpose and reshaping is to just allow the math to happen, right?
Yes, just for the dimension to match in order to get. Yeah.
So one thing that would be good, like if you had to redo these slides again, is to put one slide that refreshes people about matrix multiplication, right? So then you can show why is the dimension important, because I think once people understand that, they can understand, okay, I'm doing all these things and redoing them to end up with the right dimensions. But this already is something that makes it a little clearer to understand. Okay. Other questions or comments before we go to the code?
So one way to understand the matrix multiplication in this case is we can collapse the first and the second dimensions. So we can think of them as 16 matrix with 4 by 28. So yeah, in that case, it's easier to understand.
So after you.
Yeah.
Other questions or comments?
The mean square function.
Okay.
Oh.
Are we gonna walk through the code, or people should look at this and then go through the code themselves?
I think it's better to look at the code, yeah, themselves, because it's very complicated and it needs like running the code. Yep. So I think that's it for my presentation today.
Okay. Are we done with this chapter?
Yes. So we build the causal intentions with the dropout and also multi-head. So it's a final product of this chapter.
Okay. Questions, comments? What did you learn from this?
Yeah, so it's like it's kind of new to me because I think the computer scientists make a lot of efforts in like making the code more efficient. Yeah, it's very like elegant. I like it a lot. I need to learn how to do it as well.
Okay. Anyone else who read the chapter and thoughts? Diego?
Hi. It was good to remember about the shapes and how to split the data to multi-heads, and remember all new efficient ways of clustering data and matrix operation, not in just when you have two metrics on a paper, but in a code. It's kind of different for me, and it was good to see the implementation in the code.
Amirali, are you lost? What is this telling you from your first presentation?
Hi, thank you for your presentation. I was always foggy about the concept of multi-head. Even when I presented it, I really didn't know how it worked. And through the book, most of the parts of the book, you rarely need to search for extra materials to understand the concepts, but this multi-headed attention part was a bit complicated, and thank you, Frank, for explaining it. It was really interesting to implement attention layers to to improve, to see the to help the models see the inputs from different angles for interpretations.
And that's super important, your statement there, because that's the power of the transformer network, right? That you mask, right? But then if you look at most of the time when people explain the transformer network, they're saying it understands what, if you say the dog was crossing the street, it was knocked down by a car. The it previously was very, very difficult to understand with any other architecture. And, so that means you're processing multiple things, multiple parts of the sentences as you presented in the, earlier on, but you need to still understand what the relationships are, and even those new formations of like you remember how we discussed how the new tokens work, or when there's a new word that's being developed, right? And so speed is so important if you're going to compute all of the world's text, right? So you cannot, it's very different from maybe our test X-ray report. So I think let's try to keep that bigger picture, right? from where we start to how we are. And unfortunately, you do have either the future presenters have to contextualize those, right? So everyone always talks about like the query key and value, but those are familiar terms to us because we've already gone through them, and Amirali did a good job with that. Okay, Irene, if you're able to talk, were you able to read the chapter? Any new perceptions?
No, I did watch the video by Dr. Rosher, but no other like thoughts about it.
Mandy, I know you're new, but I don't know if you were able to catch up with the book or not.
I'm in the middle of chapter 1 still. I was trying to
Okay.
rush last night. Yeah.
Okay, that's okay. Igwe, I hope exams are done. Anything new?
Yeah, my exams are done. Thank you. I passed.
Oh.
Thank you so much. Okay, I've been able to catch up with the book, and I read chapter 3. I think I learned about the attention scores, weights, how to get the context vectors. The multi-head attention is still difficult for me to fully understand, but I think from the presentation I was able to get why we have to transpose and reshape to make the math happen. And yeah, I'll go back, look at it, and try to see how much more sense I can make of it.
Okay, anyone wants to re-explain that part for the multi-head attention? Frank?
Oh, yeah.
Or any volunteer? Ramon? Maybe.
To re-explain what the multi-head
multi-head.
attention is.
Mm-hmm.
Sure, I can try. I can share my screen. Yes.
Yes.
Okay, sure.
Yes. So actually, well, I was looking up. So Mirai actually uses the multi-head attention the way that they describe it here. So I was just looking up the code. So one would kind of expect when you're doing the multi-head attention that you have separate like attention objects. Like you have, let's say, like a list of 5 attention heads. And it seems that that might be a little bit inefficient. And we kind of have to remember that all the attention heads are doing is doing some series of matrix multiplications. So what they kind of end up doing to make it more efficient is that you have one linear layer. So like, let's say each query value and key layer is just one giant linear layer where the predictions are kind of split. So it kind of subdivides itself into the multiple attention heads. So let's say you have one layer, but one part of the layer is the first attention head. The other part of the layer is the other part of the attention head. And so by doing the projection of the inputs, so let's say here's your input, you can do the matrix multiplications on each one of them separately. And you kind of end up with the same effect as as having multiple attention heads if you do the orientations correct. So I think that's a pretty interesting approach, and it's supposed to be more memory efficient and also faster doing it like this. And so that's it. So going back, yeah. So doing the simple split of this larger linear layer, the matrix, and doing this almost like grouped matrix multiplication gets you the same effect as if you had multiple series of linear, attention heads. And I think it's a quite elegant approach. I like the way that Mirai has it set up compared to the other one because it's easier to follow. One suggestion if somebody wants to kind of understand what it does is if you can try to step through the code and see what all the outputs look like, it'll become a lot more clear. So instead of just reading the code, if you can have like add print statements of what all the shapes are, it'll become a lot easier to understand, I think.
Yeah, that's
Did
a
that
great
make
question, Ramon. Yeah. Does that help, Igwe?
Yes, thank you very much, Ramon. Thank you.
Yeah, because I didn't really understand it until I had to, while working on Mirai, I literally like added print statements of like, okay, what's the shapes doing? Because I was expecting it to be done the simple way that the book explains it at the beginning. And then I saw this and I was like, what am I doing?
Any reflections from reading chapter 3, Ramon?
So I read it a while ago, but I guess the idea with the multi-head attention, it kind of reminds me that the key to getting the models to learn in a way is just ensuring that the right series of operations are occurring. And there's multiple ways that we can kind of get that to happen. So as long as we kind of understand what the end result is, there's other ways that we can kind of implement the models that might help for our use cases. So the multi-head.
Explain that sentence. If we
So
understand what the end result is, use a medical example.
a medical oh, that's a hard one.
Okay, or anything just that makes more sense. I use medical because that's what makes sense.
Okay, so so let's say there's different ways that we can kind of like organize. Let's say you're organizing a room. There's, you know, that you just want everything to be organized near the end. But there's different ways that you can kind of go about it. And in research or any application, what truly matters is the end result in a way. Sometimes you want to optimize for time or some other components. So if you know what the true end result is and what your values are on how to get there, you can kind of swap things around to fit that. So the multi-head attention is the example of, oh, we want efficiency. But let's say for the learner's case, if you're first learning this, you might want to do the multi-head attention at the very beginning that they do, the simpler version. Does that make sense?
Yeah, absolutely. Okay. Theo?
Yeah, so thank you, Frank, for the presentation, and all the discussions has been really great for understanding this. I think the key takeaway for me was I think this slide, the last slide from Frank, really helped to understand about the positions and the different dimensions that we need to perform transpose, and how it's basically just simply stacking in the third dimension for the multi-attention head. In regards to this kind of multi-dimensional array, I do have like experience, but it's in the imaging domain, where we have, for example, like a 3D, like a CT scan, a stack of CT scans. Then we would have like a three stacks, and then it was similar to this kind of configuration. We have multiple images and multiple slices. So, and then the size of the image itself. And then if we do a transpose, you can play around with the different transpose of the different axes of the vectors of the array, and we can actually visualize what the change in the medical image would look like. So for example, if swapping the axis of the third and second, doing the transpose in that way, and then looking at the image, you would actually have like a transverse or versus an axis, axial slice, or it will translate to a coronal slice. Even you can look at like a sinogram, and it will look at, you can actually visualize it. That's my experience, but here it's mainly weights that you can't really visualize, but it's kind of, the concept is kind of similar.
Yeah, unfortunately for your explanation, what would be good, and I'm going to ask you to do this if you have the code, is to like just show that such an example, because I think it really can solidify people's understanding of, right? Because we know images, if it can be cats and dogs, and then show sort of like how you're walking down, right? So I think Ramon's explanation was very, very good to I'm also frank, right? Because it's just so hard to figure out, first of all, why are we doing this? And then see the different ways, because then from then on, you can come back and say, I'm going to remove this, or maybe this is causing something else, you know? So that would be great if you could just spend like maybe a few minutes just walking through like a medical image or just something else that we are more familiar with. Like this is the concept of learning from somewhere where you're very comfortable with to where you don't know, right? And usually yeah, that would be pretty cool.
Now?
Oh, no. I
Oh,
mean, not unless you're ready now.
Well,
Right.
I'd get like
Really?
a CT scan and then get that, then we can play around with that. But yeah, I can do that
Yeah.
the next one.
Okay. Cool. Let's see. Jamin, anything? I don't know if you're reading this book with us anyway, but let me know if you have any comments. Okay. Cool. Okay, so Yago is going to discuss the chapter 4. When are you ready, Yago? Next week or the other week?
I guess I'll try to prepare by the next Friday, but if something happen, can I just prepare by the through the one?
Yeah.
Okay.
Cool. Okay, so I'm gonna pause this.